This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about statics CE 2301, homework problems 7-1, 6, and 13. These were three problems, and the object is to find the centroids of various shapes, a line in two areas. We're going to start off with 7-1. It was to find the centroid of this line, which is defined by the equation y equals 0.2x to the fourth minus 12.8x. Okay, we start with the fact that any elemental segment of the line DL, shown right here, is composed of dx in the horizontal and dy in the vertical. Okay, just like any right triangle, the length of DL is equal to the square root of the sum of the squares, dx squared plus dy squared. So we can rearrange that as it shows in the textbook, and we come up with DL is equal to the square root of 1 plus dy over dx squared. Well, dy over dx is the derivative of this formula, dy with respect to x. And so the derivative of that formula is 4 times 0.2x to the third minus 1 times 12.8. So we can simplify that down to the derivative equal to 0.8x cubed minus 12.8. Okay, we can substitute that into this equation right up here, and we get, and if we integrate it, the length of that line is the integral of the square root of 1 plus dy over dx squared. Same as that equation. Plugging in that formula for dy over dx, we get the integral from 0 to 4 of the square root of 1 plus 0.8x cubed minus 12.8 quantity squared. Okay, now it's a wicked integral, so we would encourage you to use some sort of computational program. MathCAD, which is available in the labs, the computer labs upstairs in the CE building, or Wolfram Alpha. First time I did this, I did all the math and expanded it out to 0.64x to the sixth and so forth, and Wolfram Alpha couldn't solve it. But I found that if you'll put this formula into Wolfram Alpha, you'll come out with that length of the line from x equals 0 to 4 of 48.713 millimeters. Okay, now I need to know x bar L, and so the x bar distance of each little elemental segment is just the x bar distance of the out to that part of the formula. So I just multiply this quantity, which is the length of the line integrated, times, or the length of the little elemental part, dl, times x. So you can plug that into Wolfram Alpha or MathCAD and get a value, which I'm not going to give you because I want you to do that yourself and have the fun and experience of using one of those computational programs. Same thing with y bar L, where I plug y bar of each little element dl, and that is equal to the y at any point along that line is equal to this formula right here. So the expanded version is an integral of y dl. Y bar dl is this formula for y, 0.2x to the fourth minus 12.8x, times this formula for dl, the square root of all that. And you can also plug that into Wolfram Alpha, and you will get a number. And the final step, once you got those, you're on the home stretch. X bar for the whole line is equal to this value that you get from Wolfram alpha of XL, X bar L, divided by L that we got up here. And that's, I'm not going to tell you the whole thing, but it starts with a 2 point something something millimeters. Y bar, similarly, is equal to Y bar L from this formula that you get from Wolfram alpha, integrating from 0 to 4. Should have put that in there. We're integrating from 0 to 4. So we divide that by this length that we got for L, integrating 48.713, and you get a number that's like negative 1 something point something. You can do the math. Once you get past those integrals and get them set up, it's pretty easy. It's easy for me to say. Okay, look at number 7.6. I'm going to do even less of it because I want you to practice doing this. If you can do this, you can do the test problems. The object was to find the centroid of this sort of shaded area that's defined by the X and Y axis and this formula for Y, which is H times the quantity 1 plus X over L minus 2X squared over L squared, where the H is the starting value of Y, L is the ending value for X. So we want to do these integrals, and we're doing them about X as the integral from 0 from X equals 0 to L. Didn't write that in there. Same for Y bar A. Okay. The key is to use this little vertical strip as your elemental segment DA. DA is an area Y high by DX wide, that little strip. So Y DX is the area where Y is this formula right here. At any point along this line X, Y is that much. So multiply by H, multiply that by DX, excuse me. And my area is the integral from 0 to L, I did write it in there, of the height, which is Y, all this formula for Y, H, blah, 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 times dx. So I integrate that. The integral is equal to, integral of 1 is x, h times everything. Integral of 1 is h, is x. The integral of x over L is x squared over 2L. The integral of 2x squared over L squared is 2/3 x cubed over L cubed. Remember that the integral of x is x to the n plus 1 power divided by n plus 1. So you can do all the math, integrate it from 0 to L, and you get that the area is 5/6 h times L. Okay, you don't need Wolfram alpha to do that. Now I need my little X bar and Y bar for that little elemental strip, which is Y dx. The X bar distance is just the X value. So let's do that one first. X bar A is the integral of this formula for Y, or really for dA, which is Y dx from up here, and I multiply it by X. So that multiplies all these terms by X, and so then you can integrate that using that X. The integral of X is equal to X to the n plus 1 power divided by n plus 1, and you get 3 terms there, and evaluate it from 0 to L, and you get a value for X bar. Y bar A is a little bit more complicated because I want to multiply this value for dA, y dx, which is up here, times this formula for y bar, which is y at any point divided by 2. So I just take the h divided by 2, multiply it by the rest of that expression, 1 plus x over L minus 2x squared over L squared, and I get a formula for y bar. Plug that in here, plug in my formula for dA, which is this expression up here, dx, and multiply it all out. It does get to be quite a few terms, but it is solvable without using Wolfram alpha. You can use Wolfram alpha if you want to. Anyway, it equals y bar A is 0.4 h squared over L. Then using this exact same formula, I get y bar is equal to y bar A divided by A. X bar is equal to x bar A divided by A. And you get some fraction, something is expressed as a form of H and L. Okay, 713 is also similar. I have this shape, this area that is bounded on the left by the y-axis, on the top by y is equal to 8 millimeters, on the bottom by y is equal to 1 millimeter, and on the right side it's bounded by this formula x cubed y equals 64. Okay, this time, because my strip doesn't go all the way to the x-axis, it's easier if you use a horizontal strip that goes from y out back to y x equals 0, and therefore I want x kind of as an expression of y, and I want to integrate with respect to dy, not dx like I did in these other two programs. So I know this is all jumbled together, but follow me here. I rewrite this expression, x cubed y equals 64, as x equal to the cube root of 64 over y. I can rewrite that. The cube root of 64 is 4, and y on the bottom can be written as y to the negative 1/3 power. Review your algebra expressions if you need to. Okay, I said that we're going to use a little strip, horizontal strip, that's dy tall by x long. So dA, the little elemental strip, is x dy, which is x time, which is this expression right here, 4y to the negative 1/3 power, dy. I can integrate that from 1 to 8 in the y distance. Starts off at 1, goes to 8, and the integral of that is equal, I'll give you a hint, of 18 to 18 millimeters squared. So that's the area of that shape. Okay, now I want to know x bar A, which is an integral of x bar for the little element, the little area, strip of area, dA, is x bar dA. So x bar at any location of that strip is x over 2, where x is this, so x over 2 is 2y to the negative 1/3 power. So that's this expression right here, that's x bar. Then dA is just this expression up here for dA, 4y to the negative 1/3 dy. I combine the terms, I get the integral from 1 to 8 of 8y to the negative 2/3 power. It's because I'm taking this y to the negative 1/3 times y to the negative 1/3 is y to the negative 2/3. Integrate that, following that rule. The integral of y to the n power is equal to the y to the n plus 1 divided by n plus 1. Take this value, add 1 to it. Negative 2/3 plus 1 is positive 1/3. That's another big hint. And then I'm going to be dividing 8 by 1/3. And you integrate all that out from 1 to 8, evaluate it 1 to 8, and I get 24 millimeters cubed. Remember, I've got an area, millimeters squared, times a distance, millimeters. That's why I get millimeters cubed here. Okay, we're almost home. Y bar A is just the y distance, which is always just y at any point along that line. And so it's just y times this expression for dA, 4y to the negative 1/3 power, dy. That's equal to y to the 2/3 power. I add the 1 when I multiply y times y to the negative 1/3, and I evaluate 4y to the positive 2/3. Use that rule. I get an expression. It's like 4y to the 2/3 evaluated, integrated. It's 4y to the 5/3 divided by 5/3. Anyway, evaluate that from 1 to 8, and I get another number, and divide that number by 18, and I'll get y bar. Divide this number for x bar A by 18. So there I'm giving you really what x bar is 24 divided by 18. Pretty wicked stuff, but won't be anything this hard on the test.